Uh, Hello, participants. Very good evening. Today we have with us Dr. Jan Dragona. Dr. Jan is a senior data scientist and the principal investigator in the Physics and Computational Sciences Division at Pacific Northwest National Laboratory, we call as a PNNL lab. Dr. Jan has a PhD in control engineering from the Slovak University of Technology in Bratislava, Slovakia. And before joining PNNL, he was a postdoc at Mechanical Engineering Department at Catholic University Leuven, Belgium. His current research is focused on differentiable programming for scientific machine learning, constraint optimization, and model-based optimal control, with applications in the energy sector, including building control and power systems optimization. We are very fortunate to have with us today Dr. Jan. We'll be delivering a session on differential programming for modeling and control of dynamical systems. So I request Dr. John, please start your session.
Thank you very much for a very nice introduction. And I apologize again for mismatch with the translating
no problem.
The time zones. Should everyone see my screen now?
Yes, please.
Okay. And today's talk will be on differential programming for modeling and control of dynamic system. That is a joint work with a broad array of collaborators from Pacific Northwest National Laboratory, Aaron Tuor, Shreyang Abhyankar, Ethan King, James Koch, Zhao Chen, Soumya Vashisht, Vikas Chandan, Vencesalo Shao Cortez, Shayak Mukherjee, Mahantesh Halappanavar, and my team lead, Draguna Vrabie. So you see we have larger team, very diverse background from control theory, constraint optimization, aerospace, energy systems, deep learning, and power systems background. The purpose of this diverse group is to come together and come up with the new ways how to model and control dynamic systems based on new emerging methods and tools, primarily from computer science. Our research is primarily funded by Pacific Northwest National Laboratory and Department of Energy in the United States, whose main purpose is to progress the next generation resilient energy systems. So let me start with our motivation. First, we want to do systematic modeling of complex engineering systems and have accurate simulations because they are crucial for many areas of decision making and scientific discovery. But we are facing with striking need for improving computational efficiency and scalability of current heterogeneous scientific simulations. There are numerous software tools for modeling various kinds of dynamical systems. The simplest one, you can have simple state space models in MATLAB, but they are not accurate enough, of course, to capture highly complex systems such as power system network or thermal heat transfer in large-scale buildings. And for those, people develop custom high-fidelity simulation solvers in C++, in C, such as GridPack for power grid that has been developed at PNNL, or various libraries in Modelica for buildings. But the problem with those that they are not directly suitable for optimization and control. They are very good at simulating dynamical systems at the relatively high computational cost. In recent years, there have been headlines such as latest neural networks can solve the world's hardest equations faster than ever before. And this brings a lot of interest from across engineering disciplines to start using machine learning to accelerate physics-based models. So many of you definitely heard these buzzwords like physics informed, physics constraints, knowledge informed, neural networks or machine learning that essentially aims on bringing physics-based knowledge into structure or loss functions of machine learning models to provide them with some inductive biases towards a certain task. So we are very much in this category of researchers. We want to systematically combine prior physics knowledge to have rigorous guarantees, to be able to learn from fewer data points, to decrease the computational complexity for the inference so we can have faster answers, and to have model structures that are suitable for model-based optimization-based control. And we have various applications in building energy systems, power systems, potential applications in molecular dynamics or unmanned underwater vehicles. So that's challenge number one, system modeling. Challenge number two is system control. Once we have the suitable form of dynamical system models, what can we do? Well, we could do model priority control, which is based on idea that we do have some suitable representation of the dynamical system in the form of state space model or differential equations, and then we can formulate optimal control problem in some constraint optimization language like JUMP or YALMIP or PyOM or CVXPy that is translating the optimal control problem in constraint optimization problem, and we are solving the problem in real time. Model priority control has been very successful based on the constraint optimization solvers applied in modern aerospace, automotive, process control. That's where the model priority control emerged in 70s and take on the role of optimizing the set points and economical operations of petrochemical and pharmaceutical plants. But in recent days, many of you may be familiar with high-performance robotics, such as this Atlas robot from Boston Dynamics, who is doing fantastic parkour. He's more agile than myself and probably most of the humankind at this point. And a lot of headlines are attributing this to machine learning. That's not true. Everything is engineering and model-based optimization and model priority control. So it's a tribute to the power of model-based optimization, engineering first principles. However, the challenge becomes when we ought to deploy these complex optimization-based controllers into systems where we don't know the accurate system dynamics model, or the system dynamics model is too complicated to compute in real time, or it's not in an appropriate form or for our current solvers. And this could be large high fidelity models written in C++ or Modelica or heterogeneous compute. If we are in this situation that we have some simulation model that is considered black box simulation environment from the optimization standpoint, people have been using successfully deep reinforcement learning. And it has been deployed everywhere where you have a reliable digital twin model, and you can mostly use like discrete action space, and you can use massive amount of compute to sample this simulation model to observe the response of the system together with some scalar value reward. And then you are deploying classical reinforcement learning algorithms to learn explicit control policy that solves approximately this optimal control problem. So there is a lot of flexibility in terms of what types of system you can use. There is very little assumptions on your system dynamics properties of your form of your system dynamics model. And that allows to be implemented and deployed on wide array of systems, but probably the most successful it has been so far in computer games and board games where you can basically simulate outcome of any potential scenario in semi-brute force manner. So primary question is how can we combine the benefits of both? The performance, sample efficiency, and strong constraint satisfaction, stability, and safety guarantees of model predictive control compared to relative flexibility and adaptivity of deep reinforcement learning. But before we do that, we want to focus a little bit deeper how we are actually solving these optimization problems for control. And I will start with online optimization. On the left-hand side, let me check if I can do laser pen, where we reformulate the optimal control problem in constraint optimization problem. That's how we solve online so-called implicit model predictive control. So we start with some system measurements. If you have partial observable system, we can employ some state estimator like Kalman filter to give us the initial conditions of the system. And we may have additional control parameters as desired time varying references or time varying constraints or some price factors in the objective of the control. And we compute the optimal control actions as the solution of constraint optimization problem that can be nonlinear, can be linear, quadratic, depending on a type of the system dynamics and constraints present. And we are using specific solver. Like if you have a quadratic program, you use quadproc or some form of active set method. If you have a nonlinear program, you'll probably go for interior point time methods to obtain solution for current state in time. Then alternative approach is to pre-compute the solution beforehand. This is so-called explicit model predictive control that is being solved with parametric programming solvers. And here you want to find explicit solution that is typically parameterized by piecewise affine functions that minimizes parametric objective where x are your primal decisions and theta are your system parameters like initial conditions, references, and constraints subject to parametric constraints. This will return with explicit mapping of parameters into decision variables that doesn't require any online optimization. Therefore, it's extremely fast compared to solving optimization problem online. And you can provide some rigorous verification guarantees in terms of the memory requirements, computational requirements, and performance. However, the classical solver methods lead to exponential complexity. That's a little bit of bottleneck. So we are unable to solve any problem at scale using classical explicit MPC method just to the sheer curse of dimensionality. And the reason is larger the problem, more the constraints, and more possible combinations you have between those constraints. And by using factorization of Karush-Kuhn-Tucker conditions and exploring all of those possible combinations in those KKT conditions, you are essentially like doing kind of a brute force, analytical brute force solution. So that's not very practical, although the theoretical idea is very appealing. Can we have explicit solution that is kind of memory based? Why would we need to repeat the solution of the same problem and again with slight differences in the problem parameters? Scalable approach to obtain explicit controllers is to do imitation learning. People also call it behavioral cloning in the reinforcement learning literature, where you obtain the examples of optimal control decisions given your state measurements and other control parameters that are either given by model predictive control or other optimization based control or some human expert. And that's also offline optimization, but it's based on supervised learning, which is way more easier to solve. And basically, whole success of modern machine learning, especially deep learning, has been based on doing very efficient and scalable supervised learning for regression and classification tasks. So this is definitely scalable. And relatively high performing, but it still requires the expert controller. You need to have that data set that may be difficult to obtain. And moreover, you might not have strong control satisfaction guarantees for constraints and stability like you would have with original problem. Many people have been working on this in the recent couple of years from various control teams and trying to provide with constraint satisfaction and stability and verification guarantees on the approximation error of these imitation learning-based controllers. In the model predictive control literature, this is called approximate MPC. So a lot of progress being done there, but still the fundamental premise that you need to have original model predictive controller that can be expensive to obtain, because it means that you need to have system dynamics model in the appropriate form for the original MPC. The second machine learning group of methods is reinforcement learning that was mentioned in the previous slide that has no assumptions like that. You don't need to have expert controller and you don't need to have any assumptions about your system dynamics. You just need to have access to some system environment that you can perturb. It's very rarely that you can do this in the real world. Most of them are digital twins, so-called simulation environments that you can evaluate offline. Then what you do, you are learning so-called critic that is typically parameterized by neural network, is a black box scalar valued function that is mapping the response of the system, which is our state space, and rewards, which is scalar valued feedback from the system, into the value function. Once you have this value function, it essentially represents the aggregate behavior of your system. It's the aggregate behavior of your objective function cost to go in the optimal control problem. And because neural network is differentiable, now we can employ automatic differentiation to compute the sensitivities of this value function to provide you with the direction for the improvement of the controls. And if you take these gradients with respect to the trainable parameters of your actor, which by coincidence would be also neural network, then you have these policy gradient methods. When you differentiate the value function, then you are being provided with the update step for your second neural network to be control policy. So very flexible, but very little assumptions, which means it's extremely hard to have some theoretical guarantees on stability, constraint satisfaction, sampling efficiency. And what we want to do, we want to combine this approach, but we are going to do it in a specific way when we will assume something about this system, and that would be that it's differentiable. We can have high fidelity simulation model, but we are able to obtain the gradients of it, not only by learning black box function critic. And once we have that, we can replace the black box function critic with all the model-based objective functions and constraints like we do in model predictive control. And that's what we call differentiable control, which is based on the idea of differentiable programming that has been popularized by Julia community from MIT. I believe the first paper was in 2020 or 2019, where they introduced this concept, which is a unifying approach for combining data-driven and parametric scientific modeling using automatic differentiation. By the way, this will be a longer talk, so please feel free to jump in anytime when something is not clear, and we can have like more interactive session asking Q&As during the talk. Are there any questions so far? Doesn't seem so, but
No,
I can hear someone. So if you can mute yourself, please. Hello? Can you hear me well? I can hear Shadeo. Everyone else, you can hear me okay? Or
Please continue, sir. Please continue.
okay. So I can also hear other people. Okay, now it's muted. Very good. So if there are no questions, I will continue further to very brief and non-comprehensive literature review on differentiable programming for scientific machine learning. So yeah, the paper I mentioned started in 2019 with the title Differentiable Programming System to Bridge Machine Learning and Scientific Computing. Fantastic seminal paper that introduced a lot of new ideas how to use the tools that has been here for decades, but use it in novel way. Use it for wide array of tasks compared to how it has been used before. So automatic differentiation, it has been here since, I don't know, 80s, 70s, mostly used for like climate modeling and high fidelity system dynamics that have been written in Fortran or C++, and you had like these domain-specific automatic differentiation languages that supported only specific type of equations. Then deep learning revolution came in early 2000s, where this progress was primarily driven by what is often called democratization of automatic differentiation to the broader community by developing tools such as TensorFlow or PyTorch that are essentially automatic differentiation frameworks. Although the original idea is that you can automatically differentiate only deep neural networks, which are composite functions based on affine transformations and pointwise nonlinearities. But ever since these frameworks become more and more powerful in modeling more heterogeneous types of functions, that led to research in different kinds of machine learning architectures. So when we look in top machine learning research these days, they are not simple multi-layer perceptrons anymore. They are highly sophisticated and complex architectures like attention models, these large language models that have a lot of custom layers. And convolutional neural networks, you can also think as some inductive priors that abandon that fully connected structure that give like bridge to go closer to classical engineering methods via models like neural differential equations, where your right-hand side of the differential equation is not known, is not some polynomial expression or some algebraic expression of other kind. It is neural network. But even further than that, what has been introduced in one of these papers is what is called universal differential equations. That's also coming from Julia community, that allows you to systematically combine classical differential equations with neural networks on your right-hand side to compute your derivatives on your states. Big hit was physics-info neural networks, where the physics doesn't come in the architecture itself, but it comes in the loss function. So you have some soft constraints and you can also calculate the gradients for those. And recently, a lot of interest has been in differentiable optimization. Different teams call it in different terms, like differentiable convex optimization layers, learning with hard constraints, deep declarative networks, or end-to-end constraint optimization learning. But they are all essentially based on this idea. Let's have an optimization problem represented as some computation graph, as a sequence of computations that we can use to compute the sensitivities by using automatic differentiation. So if we change some parameter like type of the constraints or scaling factor in your objective functions, how does my solution changes? And how can I use this sensitivity computed by automatic differentiation to obtain solution? And that can be obtained offline, it can be obtained online. It really is very universal framework. And now when we have these tools for differentiating constraint optimization problems, it's just one close step to do differentiable control, because we can represent optimal control as constraint optimization. So early papers on this was starting in 2019, 2020 on differentiable model pedigree control, mostly based on imitation learning with constraints. But since then, it took the form of itself where you can obtain parametric control policies without the need for imitation. Are there any questions at this point? Okay, if not, I will go a little bit into the formalism of the differentiable programming. Especially, I will be focusing on the parametric constraint optimization problem that we want to solve in control or in optimal design, where we start with generic nonlinear objective functions with our primal decision variables x and some problem parameters psi. And these could be initial conditions, these are references or measurable disturbances, weights of your terms in your objectives like price signals, subject to general nonlinear inequality equality constraints on these primal decision variables, and something what we call here a solution map that is typically represented by deep neural network mapping these problem parameters in your primal decision variables. So this would be your neural network solution to your partial differential equation in physics-informed neural networks. But we go beyond PDEs here. We go here for ODEs, differential algebra equations, graph, network dynamical systems, to constraint optimization problems and constraint optimal control problems. So I will show you the examples of formulation in those problems. But what you have also noticed, we have this sum over m samples in the objective. So we are minimizing for expectation over distribution of samples. And this distribution is given as this data set of parameters. So you can think of it as your unsupervised training data set, right? You're provided with the parametric space you are sampling, and you want to know what is my optimal solution for this distribution of my samples that will be learned by optimizing the parameters theta of this solution map. Well, how do you solve this? Well, you need to reformulate it in a form that is amiable for automatic differentiation. And you can use the most straightforward way, which is to employ penalty method. That's basically the idea of physics-informed neural networks, that you are training some objective function and you are providing the regularizations that minimize the violations of physics-based constraints. So these are the penalties for your inequality constraints and equality constraints. And because now you have multi-turn objective, you need to have some weighting factors to provide them with relative importance. More sophisticated methods to provide you with scalar valued objective function that is differentiable could be augmented Lagrangian method or barrier methods that are not differentiable on a whole domain. You would need to have some interior point estimates, but essentially like these are the tools that could be used these days. And now you have scalar valued objective function that can be used to differentiate backwards using backpropagation algorithms the sensitivities of this computation graph. Any questions on this? Because I know that this can be a little bit dense. Okay, then I will skip forward to introducing our open source software tool that aims to provide user-friendly interface for modeling of this type of parametric constraint optimization and optimal control problems. We call it Neuromancer. That stands for Neural Modules with Adaptive Nonlinear Constraints and Efficient Regularizations. It's essentially a framework built on PyTorch that provides us with automatic differentiation. And for people familiar with constraint optimization frameworks like CVX-Py or PyMO in Python, JUMP in Julia, or YAML in MATLAB, our abstraction starts with symbolic representations of variables that are given specific names. So we have this P, X, Y, and we have some computational graph. It can be really anything. It can be differential equation. It can be algebraic equation. In this case, it's multi-layer perceptron, which is deep neural network that maps what we call input keys into output keys, basically input variables into output variables. So now we have P as a problem parameter being mapped to primal decisions X and Y. And we can train this neural network that will be the solution that needs to satisfy some objective function given constraints like this quadratic function given these inequality constraints written in very similar way like you would do it in this constraint optimization framework in higher level symbolic algebraic language. And then you aggregate all your constraints and objectives in the problem formulation. You provide the problem component, and now you construct this scalar valued loss function. In this case, simple penalty loss is being used with objectives and constraints aggregated together. And we use the scalar values loss function to train the components in here, that this case is neural network, by using stochastic gradient descent. In this example is ADAM-W, one of the standard choices these days in deep learning community, that is optimizing the parameters, trainable parameters of this component solution map. And you hand over this optimizer and the constraint optimization problem to the trainer, and you optimize this on a given data set of samples that is sampled from some distribution. And you train this offline, and you are being obtained with explicit solution map that you can now use online without the need for repetitive solution using iterative solvers. Now we have explicit solution of your constraint optimization problem. So why we started doing this software development? Because we figured out there is no software tool that would allow us to do such a thing, like differentiable optimization for non-convex problems and control. So we started in 2019 prototyping, and last 1.5 years, we start to open source these tools to the broader community. So it's still very much in the research phase, but anyone interested in differentiable optimization control, you can use it. We already have a range of examples that I will go through later. And we hope to also receive some feedback from our users on the scalability, efficiency, and maybe like some potential bugs. So how do we think of this parametric programming through differentiable optimization perspective? We think of these problems as a computational graphs, where here we have the data set that is sampling our Xi problem parameters. Here I denote it by P. And then I have this mapping, can be really anything that is differentiable, but typically it's neural network that is mapping my problem parameters into primal decision variables. And then I impose system constraints like equalities, inequalities, and given objective functions on those primal decisions. So here I have C1, 2, 3, 4. There are 4 constraints and 1 objective. Aggregate everything in scalar valued loss function through penalties or barrier functions or augmented Lagrangian. And now I can backpropagate the values of these objective functions through these constraints and objectives back to the optimizing the problem parameters. And what it allows me to do is to solve parametric constraint nonlinear optimization problems offline. And upon deployment, this brings me with orders of magnitude faster online solution compared to online optimization solvers like Interior Point. Here are 2 very toy examples on 2-dimensional problems that are test problems in non-convex optimization, like this Rosenbrock or Himmelblau problem, when you have nonlinear objective functions, often with multiple local optima, and you have these non-convex feasible region. This is linear constraint, and these are 2 elliptic constraints that create this donut-like shape of the feasible solution. So basically, you want to stay in these regions with your solution and find the global optimum. But we are not solving it for one specific problem. We are solving it for distributional problems. So your constraints may shift in your state space. They can inflate, deflate. Your shape of the objective function can be transformed from something else to something else, like from this Rosenbrock to the Himmelblau problem, but you still have one neural network that is giving you the solutions to all of these problems. So you don't need to retrain it again. You are just evaluating this online. So that's very, very powerful. Okay, so that's for static optimization, but what can we do when we have temporal domain and we want to model dynamical systems? By the way, is there any question regarding the differentiable optimization part? Okay, so if there is no question, I will go forward with these universal differential equations that have been introduced by, okay, this is a wrong title. It should be universal differential equations by Christopher Rakaukas from MIT, where the idea is to systematically combine this white box modeling that is given by known differential equation with the black box modeling, where you have these deep neural networks representing your right-hand side of your ordinary differential equations, also called neural ordinary differential equations, in a way that is a gray box modeling, but a little bit fancier way that you are combining the black box function approximators with known differentiable equations. And in literature, people called it universal differential equations. And this allows you to learn the flow maps or phase space portraits of dynamical systems with the combination of prior knowledge and black box function approximators. But you are still using known tools and solvers from numerical scientific computing community, like all the solvers, Runge-Kutta methods, multi-step, implicit, higher order integrators that have been developed in this community. So it's a nice synergy between deep neural networks, machine learning, and modern scientific computing. And this allows you to build physics-informed or physics-structured differential equation models that blend expert knowledge with black box function approximation. And what we have been working on in our team is to expand this concept to graph-structured neural ordinary differential equations. So we call this like network dynamic system approach, that has the following form. Let's assume that we have dynamical system network which is composed of individual nodes or agents, that each of them has some autonomous dynamics we don't know. So that's this neural network. Our agent xi, it's the state space of it, will be approximated by neural network parameterized by some parameters to give us autonomous system gradients of that dynamics. And this node could be a room in the building thermal network, which is connected to other rooms and they exchange heat, or this could be the source and sink or transformer in the power system network, or it can be network of unknown oscillators that are interconnected. And this interconnection part comes in the second part of the equation. In this case, it's the sum over interactions between the neighbors, xi and xj, where the interaction is given by the sparsity of the adjacency matrix. So this is the topology of your graph. And the second neural network represents the interaction dynamics. We performed the following experiment. So let's assume we have this generic network dynamical system that essentially represents structured universal differential equation. And we want to learn the dynamics of certain type of networks, given examples from one topological configuration. And then we want to generalize beyond the training data set, but not only in obtaining new trajectories. We want to test this on networks that have not been seen before, with the changing the coupling adjacency matrix, changing the topology, or increasing the size of the network. So to have scalable modeling of the network system dynamics. As a test case, we use this ground truth Kuramoto system that is relatively straightforward. We have the autonomous dynamics over here, and we have the coupling dynamics over here. And it represents relatively complicated, chaotic attractor. And what we are able to do is to generalize beyond the topology of the training data. So here is an example visualizing the 3 nodes in the network. We performed the experiments up to the network with 11 nodes, where you can see the blue trajectories. That is the ground truth model. That is the simulation of this Kuramoto system. And the orange one is the prediction of our universal differential equation with these 2 neural networks being trained on a different system with different coupling adjacency. So what we can see that, okay, we are not exactly matching those trajectories, but we are able to reproduce qualitative behavior of the dynamics on never seen network topology. So this is very complex generalization task, but adding this little bit more structure into the right-hand side of your neural differential equations does all the difference in being able to generalize not only outside of the distribution of the training data, but outside of the system dynamics itself. So this is very encouraging and potentially very powerful for modeling complex dynamic systems like thermal networks or power system networks or multi-agent dynamics. And we are currently working on expanding this problem in some practical scenarios in energy systems for modeling and control. Any questions at this point? Yeah, if not, I will move forward by quickly walking through different architectural arrangements that you can employ in your neural ordinary differential equations. If you also are familiar with state space type modeling, this is typically what we do in control. You have A, B, C, D matrices, and you have recurrences on your A matrix, and that's typically what you have for model predict control. But you can have nonlinear state space models. And in classical system identification literature, they have been called like the Hammerstein when the nonlinearity is on your input space, or Hammerstein-Wiener when you have input nonlinearity, output nonlinearity, or when you have full nonlinear state space model, that's called block nonlinear. Very popular these days, Koopman representation when you have some lifting function that maps the observables into a latent space, and you have linear operator in the latent space, and then you project that lifted latent space back to the system of observables, or just plain unstructured neural network, like a recurrent neural network type predictor. So each of those boxes now can be represented by deep neural networks. But not only that, can be structured deep neural networks. It could be ordinary differential equations. So there is a lot of structure that can be embedded in these deep learning architectures that is inspired by engineering knowledge and the dynamic systems that will help you to provide some inductive biases. And this is like higher level structure, but you can go into like the low level structure in each of those boxes when you employ some neural networks. You can also use linear algebra to constrain the behavior of your training on weights. Just a second. Close this, my second alarm clock, the regular one. So what we are presenting here are trainable weights of deep neural networks. So this gray rectangle represents one neural network that is composed of layers of affine transformations for all the Dipole-Fine nonlinearities. These are these nodes. But in classical deep learning, you are training just weight matrices. You can train structured linear maps. That's how we call them in here, and we provide open source implementation that provide you with linear algebra factorizations and regularizations that come with predetermined structure, like this orthogonal decomposition that is base of singular value decomposition. So you can have control over your singular values. That's what we show in here on the left-hand side. And this allows us for very structured and rigorous training in terms of providing the hard constraints on the matrix singular values or eigenvalues if you have square matrix. Another map we have in here is Perron-Frobenius map that also provides you with bounds on eigenvalues and further also promotes some sparsity in the structure of the learned interactions. And we have up to 30 other factorizations that allow you to do positive definite matrices, symmetric matrices, or other forms of structural assumptions like these more complex and exotic butterfly matrices. So for any deep learning practitioner that is concerned with stability and some kind of inductive biases, this could be nice addition to the toolkit. It's written in PyTorch, it's open source, and it's really just drag and drop replacement for classical weights in PyTorch layers. Okay, so that's overview of the literature, motivation, theoretical aspects, and the architectures that are behind our tools. Now I want to progress a little bit towards more application focused, where we leverage all of these tools for structured machine learning, for modeling thermodynamic systems. This is a rendering of real building at our campus at PNNL, where we want to model the thermodynamics heat transfer in the building for the purposes of control. So because we are engineers, we know the laws of thermodynamics and we know what is the structure of the physics-based model, So on the left-hand side, I have really oversimplified it a little bit, but in essence, we can obtain equations in this form, which is nonlinear state space model, where this part represents the RC, resistance capacitance network of the spatially discretized heat transfer equation. These B are the influx flows of the heat. That is also very sparse. Then we have nonlinear influence of the disturbances that are like solar irradiation through the surfaces of the building that have like different behavior when it is concrete or there is a window. We have influence of the ambient temperature where our system tries to get to the thermal equilibria, and we have these bilinear relationships of the convective heat flow equations. So this is all a graph neural network, as we see, or graph dynamic system. Can we represent it in a structured neural network? So that allows us to think in computational graphs. So here we have these weather actuators, heating, ventilation, air conditioning systems, and building envelope. This is a high-level graph. Why not to replicate that high-level graph in the architecture? And now each of these blocks is some subcomponent that is physics informed or physics structured neural network. And that's not only black box function approximator. It's way more uninterpretable. It requires fewer data points for training, and it's more amenable for transfer learning because now you can see, oh, I have the same HVAC with the other building, but a slightly different building envelope. So why I don't keep this neural network that represents my HVAC? I'm just going to retrain the part for the building envelope. And in the equation form, you can represent this as this physics structured recurrent model where the evolution of your states will be given as a composite of the dynamics of your building envelope, dynamics of your HVAC, dynamics of the system disturbances, and you may have some kind of state observer. Again, this can be neural network that is structured with prior knowledge that filters your observables, like your time series, into the initial conditions of this physics constrained neural network, and given predictions of your weathers or other disturbances and controls from your controller, you will be obtaining the predictions of your future trajectories of system states that in this case are temperatures in the building. So we've performed the system identification of this 20 zone building. So we have relatively complex system, high dimensional, and we have 20 observable temperatures that we want to mimic. We are using only 10 days for training data because that's very often the realistic scenario in this building modeling and control. We have limited amount of data or limited quality, and we want to obtain the predictions for the following 20 days by first having the validation set, and the last one is the test set. And these trajectories show classical system identification approach with